Okay, so I know that there is a few seconds delay, so I am watching on both screens. I don't need that control room open anymore. I'm watching on both screens, and I just want you to give me the affirmative on the chat bar as soon as your stream opens. So I know that there is a few seconds delay, so I am watching on both screens. I don't need that control room open anymore. And I just muted my my volume on my speaker so that you won't hear double voices this time. Just give me the affirmative that you guys can hear me. Hi guys. I see you on the chat bar. Okay, so we're going to talk about equilibrium again today, not just the definition, but what happens when you change equilibrium. And I just think it's worth talking about today all the crazy things that went on at my house, because it does relate to my personal equilibrium and how my personal equilibrium has definitely shifted and changed over the past couple of days, and I'm sure yours has too. So today, during what I call Corona Chronicles, what is this, 2.0, 3.0, whatever day we're in, I completely lost track already. We spent the entire day crafting a leprechaun trap, because apparently on St. Patrick's Day leprechauns invade your homes and they need to be trapped, and that's pretty much what went on here all day long. And it's definitely a deviation from my normal equilibrium. You know, my normal equilibrium is always crazy. I got things going on with kids, and I teach, and I work, and I'm a mom. Got so many things going on. 2 dogs, a cat, 3 kids, and I feel like I have my equilibrium in a happy place. Like I figured out how to kind of juggle it all, and then, you know, life takes a, big old turn and equilibrium gets disturbed, which is where I need to take you today. So what happens when your equilibrium is disturbed? Equilibrium in my mind is like the happiest place on earth. Like, I think of Disney, I think of equilibrium as this magical place. And then what happens when whatever equilibrium you have established becomes disrupted? How does that affect the equilibrium, and then how do you return back to whatever equilibrium it is that you're trying to achieve? Which is where I need to take you today. The happiest place on earth, and what happens when someone takes a giant LeChatelier or LeChat on your happy place, and that's where I'm taking you today. So equilibrium is the brainchild of this French chemist whose first name was Henry Louis, and his last name was LeChatelier, and I'm very often going to abbreviate his last name as LeChat or Shatty, because I'm very lazy trying to spell that, and I can't spell, but I will very often abbreviate his name. When I think of LeChatelier or I think of Shatty, one of the big things that he is attributed for is he's the first gentleman in 1899 who studies chemical equilibrium. So we need a 2-second review. Okay, LeChatelier states that when a system is in equilibrium, there are 2 things that define a chemical system in equilibrium. When a chemical system achieves equilibrium, the concentration of the reactants and the concentration of the products are going to remain constant. This is where we were yesterday, and we did a really good job of highlighting and bolding. I'm going to do that one more time. The concentration CON must remain constant. And the reason why these concentrations are going to remain constant is because the rate of chemical exchange between the forward reaction and the reverse reaction have to be equal to each other. And the way that I remember this is I think of rate, which ends with an E. Let me bold this guy. Shift bold. Rate with an E. Actually, a little underlining here. Of exchange with a E needs to be equal with an E. This is the brainchild of LeChatelier, and this is when he's talking about when a chemical system achieves equilibrium. This is his definition. And then he turns around and he says that a system, or a chemical system, let me go back a minute. When a system achieves equilibrium, I really can't spell tonight. It's been a really long day of leprechaun trapping. When a chemical system achieves equilibrium, that system is going to stay in equilibrium unless dot, 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 dot. And I'm going to go there in a second. When you achieve an equilibrium, you achieve this balance. You achieve this biology word we would use is homeostatic balance. And there's a difference between an equilibrium and a homeostasis. Every homeostasis is a type of equilibrium, but not every equilibrium has to be homeostatic. And I'm going to go into that difference in a few minutes. When I think of LeChatelier's principles, I think that this concept of equilibrium, which we should really title this and make sure we understand that over here, this is when a system is in equilibrium, these conditions. I think of equilibrium, it's not how you spell equilibrium, I think of that as, you know, like my happy place. And I got a whole bunch of clip art here. Whenever I think of equilibrium, I think of the happiest place on earth. So, actually we need a background too. I think of the happiest place on earth. Like, I think of Disney. Equilibrium is like Disney. Well, you know, before it all closed. We're gonna go there in a minute. Equilibrium is like Disney. It's like the happiest place on earth. I think of equilibrium and I think of like rainbows and unicorns. Actually, that's like a unicorn mermaid seahorse. A unicorn doing the dab. I think of rainbows and lollipops, and I think of just the happiest place on earth where it's a beautiful thing. And in chemistry, if you achieve chemical equilibrium, that's like the best thing that can possibly ever happen. It is a happy thing. And I also think whenever I think of equilibrium, there's just like glitter everywhere. So we should have the glitter in the background. Equilibrium is like the happiest place on earth. Okay, I'm going to pause for a second. Zach, yep, this is going to be review of the PDQ. I'm not quite there yet. I'm doing a little background information for you so you understand. Okay, happiest place on earth. Equilibrium. So a system achieves equilibrium and it's going to stay in equilibrium unless ... something bad happens, which LeChatelier's next statement is, well, what happens when something bad happens? So I'm going to keep going over here unless ... a stress is applied to the chemical system. And I'm going to shrink this down just a little bit. So unless a stress is applied to the chemical system. Now, I want to go back to this whole concept of you're in your happy place. You have achieved a status of equilibrium. Like, I want you to picture right now, like, you are in your happy place. Like, close your eyes. Wherever your happy place is, just channel that happy place. And you're like, oh my God, this is the greatest place. There's like unicorns and rainbows and glitter. And I'm going to stay in this happy place until something stressful happens. When something stressful happens, it like rips you out of your happy place. And I think right now, everything that's going on in the world, there is a whole lot of stress that is going on. You have completely been thrown out of your normal equilibrium that you're used to. Like, you're used to going to school, you're used to hanging out with your friends, like you're used to going out on Saturday nights and going to the movie theater and you know, like, I don't know, like high-fiving and being able to like look at each other and like, you know, touch each other without worrying, you know, you're gonna get a virus. That would have been your normal equilibrium, and now there is a huge stress that is applied. I want you to start thinking about things that would stress you out in your everyday life. And then I want you to start thinking about, well, in chemistry, like, what kind of stresses could you possibly apply? When I think of stress in my everyday life, I think of anything that is different than what I'm normally exposed to. In chemistry, when we start talking about stresses, there are 3 stresses that can be applied to a chemical system. So I'm going to go over here for a minute, and I'm going to make a bulleted list of the 3 stresses you are responsible for knowing in this class. Stresses to the chemical system: if you change the temperature. Changing the temperature is a big stress to a chemical system. You know, a chemical system that was in equilibrium, the rate of exchange is equal, the concentrations are constant. You change the temperature, you are playing with that balance. You're playing with the balance of the stability of that system. That's a major stress to a chemical system. It doesn't just have to be temperature. You could change the pressure. That's another one. That really only works if you're talking about gases, but pressure is another example of a stress to a chemical system that would disrupt the happy place. One final example that you are responsible for knowing in this class is if you change the concentration, and I will get into this later in the slides. Either today I might get into concentration, or I may get into concentration tomorrow, because this is going to be 2 parts. I want to finish in 40 minutes tonight, even if I have to split it. I'm going to shrink this down again in a minute. So the concentration of reactants, that's definitely one of them. Or I could even change, the concentration of product. Those are all stresses. Now, I think it's really funny because whenever I think of LeChatelier, I think his name is just absolutely appropriate. Because when I think of a stress, I think, you know, my life's getting crazy. It's like someone just took a giant shat on whatever I had going on in my life. So whenever I think of LeChatelier, I think, oh, that's stress. I'm like, oh, like somebody took like a big old shat on the equilibrium. And shat, I'm spelling it C-H-A-T, not the curse word. It's totally different. This is 100% chemistry approved. I think of this stress as someone taking a LeChat on the chemical system. When someone takes a LeChat on the chemical system, it's going to change that equilibrium balance. And that's where I need to take you today. Well, what happens if there's a stress and someone takes a little shat on the system? Okay, so I'm looking right now at the comment bar because I'm going to ask you a few questions in a minute. And I'm going to ask you, well, how do you deal with stress in your everyday life? Like, I mean that. Like, when someone takes a giant shot on your equilibrium, somebody applies a stress to your life, something stresses you out. I want to know, like, what are your coping mechanisms? Like, how do you handle that? What do you do? So, no, not what I meant to do. Okay, what do you do when something stresses you out? Okay, I'm going to wait for you guys to leave me a few comments in the sidebar, and I want to know, how do you handle stress? What do you do? And there's no right or wrong answer. Like, don't be ashamed. I'm going to tell you what I do in a few minutes when I get crazy stressed. So go ahead, take a minute. I'm going to wait for you. Mason, you sing in the shower? I love it. Okay, Olivia takes a breather. I see a lot of ice cream, crying. That's usually my go-to. Listen to music, watch movies, binge watch shows. Yeah, that's a good one too. All right, so let's talk. So I'm just going to go back one slide just to summarize to get you to the third slide on equilibrium. So equilibrium is this happy place. Like, it is so happy. It's like Disney. When you achieve equilibrium, you're all like, yay, that's so happy and awesome, and I'm going to stay in this state of equilibrium unless someone takes a big old shat on my life, somebody stresses me out. And these are the stresses chemistry-wise that you can apply. I think there's so many more stresses in your everyday life. And when you are under a stress, I'm going to continue this little statement over here, unless the stress is applied to the chemical system, ... I'm going to head to the next slide. When a stress is applied to a chemical system, the chemical system is going to shift to accommodate the stress. And I'm going to shrink this down, and I'm going to connect this to your everyday life. When we use the word shift, that is the chemistry way of saying, how do you deal with it? Like, how do you deal? And there's so many things that I'm seeing on the side chat bar when there's stress in your life. Like, I'm right there with you. Like, my number one stunner, like when things get really crazy, is I like break down and I cry. And then I probably lay in the fetal position, usually on my couch or in my bed, sometimes while eating ice cream. That's a big one. It doesn't necessarily just have to be ice cream. It can be anything that's fattening or delicious, or, you know, candy or cookie related. Those are all great things. I feel like that's more of like a binge eating problem, but okay. So I like to eat. That's like I'm a stress eater. I love doing that whenever I'm stressed. That would be my way of shifting. Other things that people do, I'm just taking a look over there. Who doesn't sing in the shower? Clearly singing in the shower. Never tried it, but I definitely will. especially with all these crazy things going on in the world. Take a breather. That's a big one. Listen to music. Those are all great. I like that one. Like, binge watch Netflix. It's a great one. Netflix and chill, kinda, because you're not really chill. Like, you're stressed. So, Netflix and chill, kinda ish. Those are all ways that you deal with stress. Now, here's the really important thing. When something really stressful happens in your life, and I feel like, this is just, it's really difficult to teach equilibrium not in a classroom, and it's really difficult to like not be in school, and like here, we might be out for a while. That's a big stress on you, on me, on all of us. I'm sure your parents are stressed because I'm stressed with all my kids at home. There's a lot of stressors going on. And I know that a lot of you are like, this is insane. Like, how is this ever going to go back to normal? Well, according to equilibrium, let's go back. This is your happy place. Like, you were probably ripped out of your happy place, I feel like, last week when things really started to get real in the world and you started to realize, like, this is something serious. And then there was a massive stress applied where, like, it's getting really serious and there's all these stressors that are coming in. We're dealing with this stress, or we're shifting to accommodate the stress, but the reality is, will you ever go back to your happy place the way that you perceived it before? Like, will things ever really be the same for you again? It doesn't mean that you'll never be happy again, but will you learn from this experience in your everyday life? Will you take all these things that happened, and could you ever really go back to the person that you were 3 weeks ago and look at all this and be like, pretend this never happened? You will get back into a new happy place. You will achieve a new equilibrium. We all will. It's going to happen, hopefully sooner than later, but it will happen. We will return back to a new stability, but the stability and that balance and that equilibrium that we had in this initial scenario will never be the same equilibrium that we will have after we have a stress. We are going to shift to accommodate the stress, and a new, different equilibrium will be achieved. We will all get through this. We will all live to see another day. Well, I mean, there are people who are definitely not living to see another day. Maybe I need to re-say that. But as a society and as a population and as a human species, like, we will overcome this. It will just be a very different reality when this is all said and done than from what we were living, 2 weeks ago, 3 weeks ago. We will achieve a new equilibrium. It just won't be the same equilibrium, which is very, very different in chemistry to what you're used to in the living environment. I'm going to draw for you really quick. This would be kind of like before this whole thing broke out. Oh, look, equilibrium. Like, we're a little stressed, we're a little overstressed, but we're kind of maintaining this equilibrium balance. And then all of a sudden, something changes. Like, oh, there's a massive stress. We're going to shift in chemistry to accommodate that stress. I'm going to tell you how that happens in a little bit. That's part of the LeChatelier process. And then in a little bit, we're going to achieve a new equilibrium. This is still an equilibrium. It's just a very, very different equilibrium than what we had before. It is still a happy place, but it's not the same happy place that we initially had. Probably never going to get back to that happy place ever again. Initially, we're just going to keep in a new equilibrium. And we're going to stay in this equilibrium until something else happens. I don't know when. And something else happens, and then we'll achieve a completely different equilibrium that the concentration stay constant because the rate of exchange is equal. And this will go on for a long time in chemistry, where we do have new equilibriums, but they're not the same equilibrium. This is a chemical equilibrium, which is a little bit different than what you're used to in the living environment curriculum. In the living environment curriculum, the equilibrium that you're used to is a homeostatic equilibrium. And in a homeostatic equilibrium, I need to pause this for 1 second. Hold on 1 second. Okay, sorry about that. I thought one of my children had escaped their cribs. They didn't. We're good. Sorry. They should be sleeping. Okay, so in a homeostatic equilibrium, the difference is that that's a really bad homeostasis picture. Okay, in a homeostatic balance, if this was your body temperature, and then all of a sudden someone took a giant shot on your life, and they dropped you in the middle of Antarctica, you could never achieve a new equilibrium for the human body. That's not how the human body works. The human body, like this doesn't work. The human body would need to return back to a homeostatic balance because the human body temperature needs to have a very, very specific equilibrium that you need to return back to. And if you cannot return back to this equilibrium, like this is where your body wants to, like, you know, be in the middle of the Antarctic, but you can't return back to this. When you go past a certain critical point, that becomes life-threatening. In a chemical system, like, life is not dependent on these ranges where this equilibrium is set. A homeostatic equilibrium, it needs to stay static, that balance point. That is the reason why we say that homeostasis, this is the homeostasis diagram. Homeostasis is a type of equilibrium. But not every equilibrium, is not, that did not make any, I should probably type this. This is ugly. So, let me type. Let's clean this up. This is a terrible, terrible idea. So over here, I have a homeostasis, or a homeostatic equilibrium. I'm going to shrink this guy down. And in a homeostatic equilibrium, the range, or the balance, or that where that rate of exchange is happening, this homeostatic equilibrium must return to a normal range. It is a set equilibrium point, as opposed to, let me shrink this down just another hair, as opposed to, I was not shrinking it down, I just made it larger, as opposed to what we have going on in this picture up here. In this picture, this would be a just a not a normal or a regular, but a non-specific equilibrium. In this equilibrium, the equilibrium point, or the point where equilibrium occurs, is not a set or a fixed point. You know, life is not dependent on where this equilibrium ends up, which is the reason why chemical systems can have an equilibrium in different positions. Okay, I'm going to take a minute and I'm going to pause the video, and I'm just going to give you guys a minute on the sidebar because I'm going to get into some of the shifts with you really quick and how we deal with the stress. I just need to get my dog upstairs so that he doesn't continue to bark the entire time that we are doing this. So I'm just going to put this down for a second. Start asking questions on the sidebar if there's anything that you want me to address. Okay, I'm back, and there is nothing on the sidebar, which means nobody has questions. Can I just get a thumbs up to let us know that everything is good and you are you're with me, that you're understanding what's going on? Thumbs up. Smiley faces, happy places, poop emoji, sad face, crying face, singing in the shower face, whatever face you want to make, to just let me know that you're with me. You don't have to be in equilibrium, but that you're with me. Okay. So I do have one more emoji to throw in here, just because I think it was funny. So this would be the emoji that I would use after somebody took a shot on the equilibrium. Like, this is the shot point, but then this would be a new equilibrium that is achieved once the stress has happened. So I'm gonna bring you to the front. Once this has happened, this is like the new equilibrium where this is not going to the front. We'll survive. There he is. This is the new equilibrium that happened after someone took a shot on the equilibrium, but it's a new happy place. So it's like a happy place like that somebody, you know, developed after they had something crazy stressful happen to them. And that's where I need to talk to you about. LeChatelier turns around and says a chemical system will shift to accommodate the new stress, a new equilibrium will be achieved. These were the things that, like, you do as, like, a human being, but, like, chemical systems, they don't shift to accommodate their stress by crying or laying in the fetal position or eating ice cream, anything fattening them. I've never heard of a chemical system singing in the shower. These guys will either shift to the right, or they will either shift to, I really should be typing this because this is obnoxious. They can either shift to the right, or they can shift to the left, which I'm going to get into in a minute, which would be their way of crying, laying in the fetal position, eating ice cream. Well, once you cry and you're laying in the fetal position, you eat ice cream and, you know, binge watch Netflix while singing in the shower, hopefully you feel better. That's kind of what goes on here. They accommodate the stress by shifting to the left, shifting to the right, finding a new happy place, and then they're going to stay in that happy place until something else happens where they're going to have to deal with a whole new stress, and they're going to make a whole different shift to achieve a completely different happy place. And that's kind of the idea of equilibrium, that these things are constantly changing and they're dynamic. And if you have a situation where the concentrations are staying constant because the rate of exchange is being equal, you will achieve this moment right here. But like everything in life, this is really fragile. Something comes along and can disrupt that happy place and send you spiraling. Stressor, new happy place. And then something else could happen, new happy place. The stresses that we need to talk about over the next couple of days, actually really 2 days, because this is going to be split into 2 different streams. Changing temperature, changing pressure, changing concentration of reactants, or changing the concentration of product. My goal today is to take you through changing concentration. That's the big one I need to do today. If we can wrap our mind around changing concentrations, then the other guys are kind of easy, but this is a little bit of a difficult concept to wrap your mind around, which is the reason why I'm starting off super simple and just keeping it to one shift today. So here we go. We have a system that's in equilibrium. It's going to stay in equilibrium until the stress is applied. And right now, the piece of evidence that I have that this chemical system is in equilibrium, and I want to shrink this down, is this double-sided arrow that I see. Double-sided arrows tell me that this system is in equilibrium. We have a forward reaction. That is a dirty, filthy lie. Forward reaction, we have a reverse reaction, and right now those forward and reverse reactions are equal, which is keeping these concentrations constant. This is implying that I am in a chemical equilibrium. And this is going to stay in chemical equilibrium until someone comes along and takes a little shot on the system that's going to disturb this equilibrium balance. And I'm going to do a little bit of sketching for you. So let's sketch. This is nitrogen, and according to this balanced equation, I have 1 nitrogen. So I'm going to draw this. 1 nitrogen who's diatomic, and I know that because it's saying N2. And then let's go let's go lighter green. This is my hydrogen, and I have 3 hydrogens, diatomic, 1, 2, 3. And I am going to make this a reverse reaction, reversible. We're going to talk about the reverse in a minute. And when that happens, I have 2 ammonia, so that would be like 1 dark colored green with 3 hydrogens. So 1, 2, 3. But I have 2 of them, so I'm going to sketch this again. 1, 2, 3. And that's a really awful picture, but you get the idea. Now, keep in mind that these concentrations could be different, but I'm just making a point here right now. According to this chemical, and we should really make this double so this works, but according to this chemical equilibrium, I am going to be breaking this apart, and I'm going to take 1, and this has to split. I gotta split this. I drew these too close together. Can I ungroup you? Ungroup. Awesome. Okay. I'm going to take these 3, which will make product. This entire ammonia is going to get grouped together to make product. But according to these arrows, at the same exact time, a different ammonia is coming along, and a different ammonia is breaking down, so I'm going to ungroup this, and then this guy will shack up with that guy, and then these 2 will shack up over here, and then I'm going to put this guy back. So even though, according to this equation, like things are happening, because this system is in equilibrium, the rate of exchange going forward and backward is equal, which makes these concentrations before and after constant. And it's going to stay in this system of equilibrium until a stress is applied. According to LeChatelier, well, we can stress this system. And LeChatelier says, oops, I shattered. I added more nitrogen to the system. That changes everything. That definitely changes everything. Let's kind of copy this little part in over here. Let's copy this in. Copy. And let's put you down here. This is what we had going on before. Shat comes along and goes, hey guys, I'm totally going to take a shot on the system. I'm going to add more nitrogen. So he comes along and he dumps more nitrogen into this system. When he dumps more nitrogen into this system, I now have more nitrogen. That's grouped. These are grouped. Ungroup. I now have more nitrogen. It's a lie. This is not how this is supposed to go. I need 1 nitrogen with 3 greens, light greens. So I now have more nitrogen, which means I can make more ammonia. So like ungroup, ungroup. I can make more. And when there's more of these that are being made, this back end can't keep up as fast with this production. I am taking a giant shot and stressing this system out, and the system goes, hold on a minute, this is really not okay. Like, I need to eat ice cream, I need to cry, like, I can't believe you just did that. You disrupted my balance, you disrupted this rate of exchange that was equal, the concentrations were constant, and now you just changed everything. That is the concept according to LeChatelier. I need to teach you, well, what does the chemical system do in this little story or scenario? Because these chemical systems, they don't cry. He doesn't cry. Like, no, he can't cry. He's not going to binge eat ice cream. Okay, he's not going to, like, sing in the shower. Da, 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 da. He's not doing that either. You know, like music notes and stuff. He's not doing that. He says that chemical systems are going to react to this change by shifting left or shifting right, and that's what I need to show you right now. So for the sake of note-taking, I'm going to provide you with steps, and I'm going to clear this entire thing out, and I'm going to blow this thing up so I can see it a whole lot better. I'm so sorry, Henry. Okay, I'm going to blow this up, and I'm going to start giving you steps to talk about how do I know how this is going to shift. Let's bring you to the front because I like to see your face. Order, bring to the front. And here we go. I want to do at least one concentration shift with you, and then I'm going to have you do a couple tonight, you know, when the stream ends, and we're going to go over them next time, and I'm going to add some more stressors in because I really want to finish this stream in about 45 minutes. Not like 45 minutes from now, like 45 minutes total, which gives me about 9 more minutes. Okay, step number 1, when I am applying stresses. The first thing that I need to do, so you're writing steps down in your notebook right now. Step number 1, I need to cut the reaction in half. Cut the reaction that's not in half. Cut the reaction on the arrow, which signifies to me the 2 different sides of this chemical reaction. So this is step number 1. I'm cutting this reaction in half. And for those of you that like color coding, because that's like your jam, we're going to color code the steps. So here we go. Step number 1, let's cut the reaction in half on the arrow. Step number 2, and I should do this in a different color. Step number 2, I am going to assign the initial stress, and I'm going to color code this as well. Assign the initial stress. Here I go. Blue. Huh. These numbers are not working. Why isn't this changing to a blue? There we go. Okay, assign the initial stress. If I go back and I read, like right now this system is in equilibrium, and it was going to stay in equilibrium until Henry came along and was like, oops, I shouted. I added more nitrogen to the chemical system. This is my initial stress. And when I add, that is an increase. So adding is an increase. So over here, assign the initial stress. If the initial stress right now is adding, that would be an increase in concentration. If I am removing, which is what we're going to see in you know, either the end today if I have time, otherwise next time, if I am removing, that would be a decrease in concentration. So over here, clear as day, they're telling me I am adding nitrogen. I am going to assign the initial stress. I'm going to find the nitrogen in my equation. Like this is nitrogen, that has nitrogen, but this is ammonia. Like that's a compound. I want plain old nitrogen according to what LeChatelier said over there. So I'm going to assign my stress. I find the nitrogen and it says adding. So I am going to assign an increasing arrow. So when I add increased concentration, we would represent that with an up arrow. And if I am removing, I would represent that with a down arrow. And in this little story with LeChatelier, I am going to be adding, which means I'm increasing. Step number 3. Here we go. Step number 3. And I'm going to go green. Step number 3. I am going to go to the opposite side of the equation, and I am going to assign the same direction arrow as the initial stress. I'm going to explain why that makes more sense in a little bit. If not today, I will get into the more detailed explanation as to why all these things are happening in the next stream. I just want to show you in this stream like how it's done, and then we'll get into the more complicated discussion of why it is done that way, which is at least like another 20 minutes worth of discussion. I'm not doing that right now. We're going to cut it in a few minutes. I go to the opposite side of the equation, and whatever is on this opposite side, this was my initial stress. I go to the opposite side of the equation, so like opposite side of the equation, and I am going to assign the same stressor. So like this stress, that was an up arrow. So like this side is going to experience the same stress as before, as the other side. So here I go. This guy is going to get the same experience. There's going to be more of that ammonia. And I'll get into the why and the how all that happens next stream. Final thing you need to do here. Actually, like the second to final. So penultimate. Those of you who are studying for your SATs. SAT word for you. Penultimate. Second to last. Okay, let's go red, orange, yellow, green. Let's go purple arrow. Okay, so purple. Everything that is left over. Everything that is left over in the equation is going to receive the opposite sign arrow. So I'm going to pause for 1 second. I'm just going to let you all get that in your notes and write that down. And then I'm going to wait for you. You're going to give me the thumbs up so I know you're ready, so I can explain to you what I mean by that, because that for some reason confuses people. So when you get that written, write it down, give me the thumbs up so I know we're ready. Okay. Alright, so the final thing I'm going to do here, or the second to last thing, because there's one more thing that needs to happen. Whatever's left over, I assigned an arrow here, I assigned an arrow here. Whatever's left over, doesn't matter. There it is. It is going to receive the opposite stressor, or the opposite arrow. And I'm going to get into more details to what all these arrows mean the next stream. So here I go. Whatever's left over gets a opposite sign arrow, and in this case, it would be a down arrow. The next thing I'm going to look for is I'm going to, in step 5, I am going to evaluate the overall change. I want the side that experiences the largest percentage increase. I want to determine the side that experiences the largest percentage increase. So I'm going to make this teal. Let's go orange. Okay, I'm going to make this orange. I'm going to evaluate both sides here. Like, this would be an up and a down, and like, you know, that would be like 50% up, 50% down. So like that would be like a 50% increase. So I'm going to probably type this in orange. Over here, this side experiences a 50% increase. Whereas on this side, I'm just going to copy and paste you. On this side, I understand that there's only one arrow, but like one arrow and they're all increasing. This would imply that this side experiences a 100% increase in terms of the arrows and the stressors. Whichever side experiences a larger percentage increase is going to be the side that we are going to shift to. And in this case, this is the hardest part of LeChatelier's principle. You need to know your left from your right. In this case, the right is the side that is experiencing the larger increase. The final thing that would happen here is that this chemical system would shift to the right to accommodate the stress and achieve a new equilibrium. I'm going to shrink this down. shift to the right to achieve a new equilibrium. Now what this means when I shift to the right is that this reaction is going to proceed more strongly to the right. Right now, the way these arrows are drawn, they're equal. What this would look like is we would have a forward reaction and we would have a reverse reaction in equal proportion if we were in equilibrium. But in this case, this reaction is going to shift to the right, which means that we are going to have a stronger forward reaction momentarily as we now accommodate that. That would be the equivalent of like eating ice cream, like laying on your couch in the fetal position, like watching Netflix, crying. That's what's how, oh, we're going to shift to the right. We're going to experience a stronger forward reaction. The reverse is still happening, but we're going to have a stronger forward reaction momentarily, and we will get into a new equilibrium. Okay, I'm looking right now at the side chat bar, and Audrey is saying, where did I get the 50% from? Over here, I have two categories. I have the nitrogen category. So this is like 1, like the nitrogen's increasing. So this is like increase. This little category over here is increasing. And on this side of the equation, I also have simultaneously a decrease. So like I got two identities. I got the nitrogen identity and I got the hydrogen identity. One of them's increasing, one of them's decreasing. So what I am referring to here is that like when one's going up, the other's going down. I am looking at this from a percentage of increase. Only one of the two identities on the left-hand side are increasing, and I would refer to that as like a 50% increase. Like only half of those things or half of those chemicals are experiencing an increase in that part of the equation. As opposed to if I go to this side, I only have one chemical identity. Like I only have nitrogen. And I only have ammonia. But all of the ammonias on this side are increasing in concentration. I am just making more ammonia. And there's one component, and that component is increasing. So I would refer to that as a 100% increase because 1 out of 1 are increasing. And take a minute and just pause for a minute, because I feel like, Audrey, that is definitely something people struggle with. So like ask me, like if you still can't wrap your mind around that, like tell me, otherwise give me the thumbs up that we're in a good place. Okay, this is going to be the point where I feel like we pause. We did one. I'm going to give you like maybe like 2 or 3 of these to practice. And then we're going to stream again tomorrow. I'm going to go over the 2 or 3 that you practice, and then I'm going to introduce a temperature shift, and then I'll introduce a pressure shift. We'll follow that up with some practice. I have a pogo on equilibrium and LeChatelier's principle that you guys will work on, print, save in the book. So when I see you again, I can take it from you. Otherwise, this is the point right now where we stop and we pause. So, and we're going to call it a night because I don't want to overwhelm you. This entire concept can be extremely overwhelming if we don't take it in pieces and segments. And I promise you there will be a conversation of what will those arrows mean in a little bit more detail in another stream. So I'm going to call it a night. Just give me the thumbs up that we're all in a good place. I'm going to be posting to the website probably like in the next like 15 minutes, something for you guys to work on, like 2 or 3 of these where I'm going to ask you to predict the concentrations, the arrows, and whether you shift left or right. So take a minute, give me thumbs up, smiley faces, or otherwise if you're like, I have no idea what the heck just happened, then give me the face that you don't understand. It usually kind of looks like this. It looks like this. You're like, peep, 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 in class. And usually, like this is you, but usually it's more like your head's like turned to the side and you're like this. Deep, deep, deep. What? There's your neck. You're like, I don't get it. So if that's you, and you don't get it, that's totally fine. Shoot me a text and remind if you don't want to post it on the sidebar because you don't want people to know. Otherwise, we're in a good place. Give me the thumbs up, or if you need a little bit more explanation, shoot me a text and remind. I'm going to call it a night now. Um, I like the smiley face. All right. I hope you're all doing well. I miss every single one of you. I can't believe that we're in this position, but guess what, guys? This is where we were right after the February break. And then we started to hear about Corona, and you guys were like, ah! But we were still like in a homeostatic balance. And all of a sudden, like this, someone took a shot on our life. And right now, we're kind of spiraling all over the place. But I promise you that we will shift and we will accommodate. There's going to be a whole lot of ice cream eating, binge watching Netflix. We're all probably in the fetal position on the couch, singing in showers, not together because there's social distancing. And we will be in a happy place once more. This really is stinky. That's supposed to be a poop. It's a horrible sketch of a poop. It's really stinky right now. But I promise you that we will all be in a good place soon. So, I will see you all tomorrow, same place, same time. And I will try to stream a little bit earlier in the day next week because I will be able to have someone hang out with my kids so that I don't have to worry to not do this till 9. So, until next time, see you tomorrow.